So thank you for giving me the opportunity to speak here, and also thank you for the introduction. I hope within the next 30 minutes I can bring you up to speed on the methodology of INSAR and how it's combined with GNSS data, and some case studies. I want to show you the tectonics of the Pamir in Central Asia. So as you all probably know, in satellite interferometry is a methodology which is quite young. It exists only since the late 80s or even early 90s, but currently our community is undergoing a boost, which is mostly due to the Sentinel radar satellite mission organized by the European Space Agency. This mission is running since 2015, and it really boosted the data load that we can use for our tectonic research. And this also gives a tremendous advance in terms of sensitivity of what we can observe on the ground. And this is what I want to bring closer to you in the next half hour. And I think one figure that shows this very nicely is high-pass filtered interferometric data of the Ridgecrest earthquake in California in 2019. That's what you see on the left side. So it's a co-seismic interferogram which was high-pass filtered, and by doing so you can really highlight fractures and ruptures and then easily digitize that to obtain a fault or a fracture map from this particular earthquake, also with an immediate idea of the slip sense of the fractures or the faults. So this is a really quick way and cheap way to do field work in your office and get an idea about what has fractured or ruptured. And I think this map also shows that what we already know, but now we see it very clearly, is that a rupture is not just a single linear planar rupture, but it's really a complicated thing which causes also ruptures on adjacent faults or adjacent weak structures. And I think by seeing that, we really have to revise our idea of what an earthquake actually does to the crust. Before I show you my work in Central Asia, a quick introduction to the methods. So we already have seen in the work of Yarif how GNSS or GPS data works like. So I go very briefly over that. The basic idea is that you repeatedly measure a certain reference point on your hopefully basement rock, so a stable reference point, and you obtain accurate daily positions. And if you do that repeatedly, then you obtain time series which give you an idea about the behavior of that point over the years in 3 directions, which are usually east, north, and the vertical direction. And now the trick that we have to apply to these time series is extract this type of motion which is caused by the process we are interested in, because usually you have many processes overlaying in such a time series, and that's shown by this sketch here, that we have a certain shape in our total or footprint of our total signal. And now the question is, do we want to get an idea about a certain transient signal? So this could be a volcanic inflation or some kind of silent slip on a thrust fault. We could also be interested in some annual oscillation terms due to the seasonal heating and cooling of the rock or the near surface. Or, and now in my case, it would be the interseismic rates, the tectonic rates during the interseismic part of the seismic cycle, where we assume that these rates are linear. And then we can complement the GNSS data using INSAR data, which is an abbreviation for interferometric synthetic aperture radar data. And here the basic concept is that we acquire radar imagery of our Earth surface before and after a certain event. And if this event changed the shape of our surface, we can measure that by actually looking at the phase difference between these 2 radar imageries. So radar data is complex data, which contains an amplitude value, which tells you something about the backscatter energy that's returning to the antenna. And then we have this phase. And if we look at the phase change, we then see if the crust has moved away from the satellite or has come closer to the satellite. That's this range, increase and decrease. The problem with the radar interferograms is that the phase is cyclic. So whenever we reach 330 degrees, We jump back to 0, and this is shown in our interferograms as fringes. So you see an example interferogram to the right, of which I will talk later. This is showing an earthquake in the Pamir. And you see now very dense fringes close to our rupture source, which I marked with a black line. And you have not so dense fringes when you go away from the source. And these fringes you can read as contour lines. So when they're dense, it means that the surface gradient is the surface deformation gradient is very steep. And if you come away from the source, this gradient is not so steep anymore until it vanishes. And each of the fringes is equal to a few centimeters of this range change, and it depends on the wavelength of your radar satellite. There are many pitfalls with INSAR data or problems, or and I want to list them quickly and give you some ideas how you can overcome them. So if I go back to my interferogram, you see that I have noisy areas, and they are usually at places where you have snowfall or vegetation changes, rapid vegetation changes. And both of them, they cause that your, let's say, resolution cell on the ground has changed. And then you don't have good conditions anymore for interferometry. If you want to overcome that and look at earthquakes that happen in a rainforest, for instance, then you have to go to longer wavelength data, for instance. Then there is this phase ambiguity, which causes, where we have to add another step called unwrapping, which is basically counting all the fringes that we see here. But that's already a first step of interpretation, particularly when the data is noisy. It's sometimes hard to correctly count these fringes. And here we really need GNSS data or another kind of ground truth data that we can embed our observations and cross-check if our signs are correct and so on. And then, as already mentioned, the range change that we see, it's in line of sight, which is a one-dimensional measurement. And due to the right-looking nature of the satellite and the near polar orbits, so they're close to our polar, it means that our satellites are most sensitive to changes which go along east-west direction or the vertical, and they're least sensitive to the north-south direction. And here the trick would be to combine several satellite views, and then you can extract 2 or 3 dimensional observations. Then we also have a lot of artifacts in our data, and that's particularly important when you look at these small scale rates in the interseismic part of the seismic cycle. And 2 of them are atmospheric signals. I show them here as cloud fronts, which sit along mountain ranges, or also the topography that also causes fringes. So we need very accurate and up-to-date digital elevation models, and also water vapor and air vapor pressure models to predict these atmospheric contributions and mitigate them. And now when we reach these really high resolution, if our data now is so high resolved, we also start to see processes which we have not seen before when we looked at GNSS data, and that's what I show in the bottom left figure. Now we do not only observe tectonic processes ongoing, but also processes which are have their source in the near surface, so in the first few meters of our soil or surface. And they're often due to water content or the moisture within the vegetated area. So again, we need to have independent data and do a systematic interpretation of our observations. And then I already mentioned that the archive is quite short, so we have to compare our observations to geologic data so that we can tell something more about that. It's not just recent what we observe, but it's something which is stable over time. And we have to aim for long-term missions, so satellites which last for 5 to 10 years. The temporal resolution is a bit more than a few days today, so 6 days is the minimum. And if we want to observe processes which go faster than that, like the first post-seismic stage of an earthquake, we have to integrate other instrumental data which has an even higher temporal sampling. And then I also mentioned that we are collecting big data now. So we're talking about 10 meters of resolution every 6 days. So we have to have a way to automatically process the data in order to really extract the scientifically interesting parts of it. So something that comes for free in the radar imagery is the amplitude data, which we can treat as an independent measurement actually and do some offset tracking, or maybe you know it as amplitude matching or intensity cross correlation. This is like an add-on to our interferograms, but it's only helpful if we look at big rates or big offsets. So the signal to noise ratio is at 10% of the pixel size. But the benefit is really that we get north-south observations in this direction here. And I show this again with our earthquake interferogram that we have seen before. I lose the resolution close to the source because the fringes, they become so dense that I cannot resolve them with my sampling, my spatial sampling rate anymore. And this is where I can benefit most from the offsets observed by the offset tracking methodology. Plus I get this additional direction in north-south, which complements our line of sight measurement so well. Okay, a few words for the modeling before we go to the Pamir. So we have our observations now, but we want to learn something more about the source that caused these surface displacements. And how do we do that? I show you one simple example, which is a rectangular dislocation in an elastic medium. So we assume our crust is behaving elastically, and then we apply some slip on a rectangle, which we put somehow in our crust. And we need 10 parameters to describe this process. So we have the dimension of our slipping plane, we have the slip itself, we have the position and the orientation. And then we need one more parameter. In this case, it's the elasticity for the media. And then we can predict displacement on the surface. So I hope this also answers the question of Sarah. So these are the parameters that we are interested in, and often we don't know all of them and we have to constrain some of them. So any additional information which tells us something about the geometry or the fault length or even rheologic properties, if you want to make the model more complicated, it helps. Of course, we can upscale that problem and create very complicated slip patterns like I did for this Pamir earthquake that I show you later. So we can add or connect a lot of these rectangles next to each other and try to increase the resolution and also try to propagate data uncertainties or also the spatial sampling of our data points into our model. And if we then, during the interseismic stage, want to have an idea of the seismic potential of a certain fault, it just scales with the fault size and the slip deficit. So this is what you have seen in the talk of before. So now to the Pamir. What you have to know in terms of tectonics of the Pamir, I want to show you first. So the Pamir is located at the western end of the Himalayan syntaxis, and it is arcuate shaped, as you can nicely see here on that figure. And this is due to the indentation of the Indian spur. So we have this Indian spur down here, which is pushing northwards into Eurasia. And before the Pamir existed, we had this very big basin in here, so oceanic basin, which has been annihilated at the northern front of the Pamir, where the Pamir now connects to the so-called South Tian Shan over here. The GNSS rates, as you see in arrows here, they show nicely that a third of this northward indentation of the Pamir is more or less accommodated along this northern front. And this front is called the Pamir thrust system. The Pamir thrust system elongates into the Vaksh fault further here, and from it, there forks the Darvas fault, which is a sinistral fault, whereas the other ones are dextral transpressive. And the Pamir itself is separated by the Sares-Karakul fault system, which is also a sinistral transtensive system, and where this earthquake in 2015 occurred. So what I want to show you over the next 10 minutes are 3 different projects. So first, how we derived interseismic slip rates for all these key faults, which I put here or shaded in gray. And then So that's basically, it's GNSS, or it's based on GNSS observations. But then in a second step, we created an INSAR rate map, and that's really ongoing work now, where we look at the kinematics in this Tajik basin. And finally, I also discuss what we found in the modeling of this Pamir earthquake. And the red lines, they show new GNSS data that we collected with the idea to resolve the kinematics across the most important faults in the region. So with the interseismic fault slip rates, I directly jump to the results. And what you need to take home from this sketch here is that all these faults, they show dextral transpressive or sinistral transtensive motion of 1 to 2 centimeters per year, which is really high for continental setting, except maybe the Saras-Karkul fault is a little bit slower, showing sinistral transtensive motion. And the most kinematically most active area is this triangle here, which is called Peter the First range. And here we see extrusion of mass into the Tajik basin. We basically observe this extrusion also in the West Pamir. So when we have a closer look at the GNSS rates, we see that the East Pamir moves northward as a whole, so it's internally relatively stable, where this West Pamir collapses and extrudes into the lower elevation Tajik basin. And now coming back to this really active triangle, when we compared our GNSS rates on this particular profile to geological cross sections of Lukash Gawala and also the seismicity of Sofia and Kufner, we then could come up with a nice interpretation of what's going on here. So from the seismicity, we see that most of it occurs actually in the bedrock, in the lower-lying bedrock, whereas on top we have these Cenozoic and Cretaceous and Jurassic layers, which are there or are sedimenting since these oceans, when these oceans still were present. And it seems that on this very lowermost Jurassic evaporates, which are which have a low friction, it seems that this whole material is really extruding, or it's sliding, gliding into the Tajik basin. And this is why the seismicity is not within the sediments, but rather down there. And from our thrust fault modeling of this Wachs fault here, we also found a very shallow locking depth, which is in agreement with what we see in the geologic data. So when I say this West Pamir collapses into the Tajik basin, which is over here, what happens then in the Tajik basin? To better understand what's going on there, we calculated INSAR rate maps. So we took all Sentinel data that's available in this region since 2015, and we created time series of it. And by time series, I mean that now for each pixel on the ground, which has in my case has a resolution of 400 meters, we obtain range changes over time. And this looks now very familiar to GNSS time series, as I've shown you before in the beginning. So you see that's this is the width of 1 year, and we can even now identify like an annual behavior of particular points. We could also identify offsets due to smaller earthquakes. Yeah, and we can do that now in 2 look angles. So we have in red, we have descending look angle, and in blue, we have a so-called ascending look angle, which are nearly perpendicular to each other. And then by adding some constraints from the GNSS data, we then can resolve our rate maps into an east-west component and a vertical component. That's what I show you here for the Tajik basin. And you see that the pattern of these 2 maps is completely different. And this is due to the fact that the shallow processes now, they play a big role in the vertical resolution of our data. So whatever I've marked here with shaded polygons are agricultural lands classified by optical data. And you see that in most of these regions, I have a heavy subsidence. So I can conclude from that the subsidence is due to water extraction or irrigation. So I can ignore it when I try to make a tectonic interpretation of this data set. What we also observe is heavy, really significant uplift in the Western Pamir of more than 1 centimeter per year. So this is due to tectonics. And apart from that, in the horizontal, we have very strong westward motion in the eastern basin. So that's really the West Pamir now moving towards west. The whole Tajik fold and thrust belt is also moving to the west, but it's all of a sudden stopped at this particular feature here, which is the Babatak fault. And also we see a very sharp color change or ray change along this line here, which is the iliac fault. And that's a continuation of the Vaksh fault, if you remember the Vaksh fault from before. But we also see a multitude of other processes, like this is a salt fountain, which has very high extrusion rates. And then we see this tiny earthquake that I mentioned before in this time series. So this is a very nice thrust fault, plus many more things. And the interpretation of the data is really ongoing now. We can also look at profiles crossing the basin, like for instance this one. And again, we can do the same exercise as before and compare it to high resolution geological cross sections. And now it becomes really interesting because we can compare topography, east, vertical rates, and also the geological structures that we see here in this fold and thrust belt. And you see that the data set is really complicated, and it's not so easy to figure out which rate change is caused by what, if it's slope sagging or if we see some kind of rotational effect of some poorly consolidated material. So I will not tell much more from that, but it's really interesting. Now you can tie the rates to certain structures at depth. And I want to highlight one particular feature, which is the difference of kinematic behavior of faulting versus folding. So on the left side, we have these west dipping faults, and on the right side, we have these east dipping faults. I don't even know how to pronounce it differently in English. And what we see is that in the east and the vertical, we have an in-phase behavior in the rates, in the faults, but it seems that this behavior is out of phase in the faults with a T. And also on the faults, we have a very smooth behavior, and in the faults, we have this shark teeth-like zigzagging of the rates. And the final figure to that project is a close-up of the iliac fault. This one is really important because it's so close to Dushanbe and poses a threat, or it needs to be well studied in terms of seismic hazard analysis. What we see here when we look at fault cross or fault perpendicular profiles across the fault strike, we see that the INSAR east component changes drastically within the first 2 to 4 kilometers, or in a corridor of 2 to 4 kilometers next to the fault. And from that, we can already conclude that the locking depth must be really shallow. And probably it's even creeping. I cannot confirm that, but I suspect it's creeping. The problem is that my data set is heavily filtered, so it might be that a step function across the fault, I cannot really resolve it with my data. And again, if we look at the cross section, we again see everywhere these evaporites. So what I think is that the whole basin is actually just sliding horizontally on these evaporites. And again, the seismicity is in the bedrock. So what does that mean for seismic hazard analysis for Dushanbe? It's known that there are magnitude 5 or maybe even 6 earthquakes in the vicinity. And of course, we would like to locate the strain and check where the strain is actually accumulating. But it's a bit depressing that my conclusion now is that from our surface observations, we cannot really tell, because we have this decoupling. It's like a horizontally decoupled layer. And I believe that the strain is mostly accumulated underneath at bedrock. So we have to find another way to look at the seismic hazard in that region. And now the final project is this central Pamir earthquake that ruptured in 2015. You have seen the interferograms already and the pixel offset, so I will not tell more about them. But our final slip model showed that we have a 80 by 30 kilometers sized slipping plane from the hypocenter, the whole earthquake rupture towards the northeast. And we had slip of around 3 kilometers at maximum, mostly at the surface. We then also went to the field to cross-check or to get some ground truth of our observations. And because the area is so heavily or hard to access, our field team only could make it to this region here, where we expected slip of around 1 meter. And this is what we found. There was no clean rupture on the surface, but there were a lot of en echelon secondary features and pressure ridges and so on, which overall, when you do the fault or do a proper mapping, you see that the strike of these features, it aligns nicely with the focal mechanism and also the faulting or the rupture direction as we model it and observed it in the INSAR data. So this was a nice agreement of field observations and also radar interferometry. Yeah, so now leaving the Pamir and thinking on a bigger scale, there was one question about standardized seismic hazard maps. What could be the way to go there? And I just want to show you what INSAR can contribute. This is work done by the Leeds group, Jonathan Weiss et al. And they did a similar thing as I did, but on a much bigger scale. So they analyzed the GNSS data, they got the GNSS rate field of the full Anatolian block, and they compared it to INSAR time series in both look angles to then derive east-west rates and also vertical rates, and then finally to construct a strain map of the full Anatolia. And when you compare that strain map to the seismicity, you see it's quite a good agreement that where you have the high strain regions, this is also where your earthquakes occur. Yeah, so like on the eastern Anatolian fault and of course also along the northern Anatolian fault. And this can of course be extended worldwide or at least to the areas of high strain. And this whole project is mostly done by automatic data processing because we're talking of terabytes of data. And I think it's a great result, which will give us more knowledge in the future as well. But now, when we have these strain maps, how do we continue now? So I think these strain maps, they will become quite reliable thanks to GNSS and INSAR data. But it's a bit frustrating then when you think of where the rupture actually will take place. So how does the strain translate into ruptures? And that's not so easy. And that's shown by this figure here, where you see a strain map color-coded in red and yellow, derived from GNSS data in New Zealand, and then you compare it to the surface, really complex surface ruptures of the Kaikoura earthquake in 2016. And most of these fault segments have been unmapped, so nobody knew. I mean, everybody knew there is a lot of strain, so there should be an earthquake soon, but where it happens, nobody has an idea. So this, I think this points towards the limits of earthquake prediction, kind of. But there is hope. At least in the instrumental sector. And here I just showed two figures of bigger earthquakes of the last years, which is the Iquique earthquake to the left and the Tohoku-Oki earthquake to the right. And what you see here are GNSS time series prior to the earthquake. And all these time series of stations close to the rupture area, they show a rate increase prior to the main event. And this increase happened a few months or weeks before the earthquake. And the same you see here, you see very nicely in the median velocity of all these Japanese GNSS stations. So I hope or I believe that with denser instrumentation, we can do a similar exercise also maybe to continental magnitude 7 earthquakes. But we really have to go to the denser instrumentation. Yeah, that's it. So coming to the conclusions for the tectonic geodesy or the INSAR and GNSS data, we now reach a resolution of a few meters and a few days. So that's great. But what's also important is that if we want to derive these really nice INSAR rate maps, we also have to have high quality GNSS data, because we need this three-dimensionality to correctly tie our rate maps to the ground. And that's particularly important for looking at small signals, at interseismic signals, at long wavelength strain build-up signals. But once we have these maps, then they really show a lot of interaction between tectonic and near surface processes. So if you want to interpret them correctly, we have to have a systemic way how to approach the interpretation. And if you want to tell something to your grandma about the Pamir tectonics, then tell her that the Pamir is advancing en bloc northwards, but it also exhibits this westward crustal collapse towards the Tajik depression or basin. And the faults bounding the Pamir, they exhibit really high slip between 1 to 2 centimeters per year. So that's exceptionally high for continental tectonics. And in terms of seismic hazard assessment, so I also discussed that because it's part of the Edith ideas or wishes. What I think is that the link between the regional strain field and the fault activation remains unclear, and probably we will never find a way to get through this. But we have this the boost of high resolution instrumentation, which at least might hint to the timing of the earthquakes. Okay, so that's it. Thank you.